Welcome to all. Uh, in this session, we'll be discussing mass transfer in bioreactors. This is in continuation to the previous topic of the general concepts of heat and mass transfer that is discussed in the last class. So, let me share the screen now. So mass transfer in bioreactors. When we discuss about that, we have to understand what. Okay, you know what is the general concept of heat and mass transfer, but mass transfer specifically, when we are talking about it, mass transfer occurs in mixtures containing local concentration variables. Just like that of the heat transfer, if there is a high temperature, there is a dissipation of that temperature to a region of low temperature. Similarly, in the case of a mass, if there is a high concentration of mass somewhere, that may be a gas or oxygen, or like gas like oxygen, or some nutrients in the medium, etc. Wherever there is a high concentration present, there is a tendency of that that mass from the region of high concentration to a region of low concentration. So the mass transfer plays a vital role in many reaction systems. Wherever you are using such oxygen or oxygenation or aeration systems, or additional media or ingredient addition, wherever if you are applying something additionally at high concentration, then you have to consider these mass transfer concepts. If, for example, the mass transfer of oxygen from the bubbles in a fermentation broth is low. So consider such a case where the bubbles is actually there present in the medium, and if that transfer of oxygen from the bubbles to the actual metabolism site, that is the intracellular part of the cell. So okay, so if you that transfer rate is low, then the rate of the overall cell metabolism can be dependent upon the rate of oxygen supply from the gas phase. So you know that if there is a limiting factor for every reaction, if there is a limiting factor, that will become the bottleneck, so that the overall rate of the reaction will be limited by that limiting component. That is the law of minimum. So if for any reaction or for any step, wherever such ingredients are involved, or gas is involved for a process, and if there is a limiting factor, that limiting factor will decide the overall rate, because without that limiting component, the further products cannot be produced. Similarly, if the oxygen transfer is that is low, then what happens is that the overall oxygen transfer and subsequent metabolism will be limited by that limited supply of oxygen. So this can be overcome only by external oxygen supply. So if there is not sufficient, and a simple case is that of the oxygenation of the COVID patients, in which we know you require external oxygen supply, because the normal oxygen transfer from the air is not sufficient for them. The oxygen transfer efficiency in their lungs will be limited, and in that case, a high concentration of oxygen, or purified oxygen with more concentration, with more partial pressure of oxygen, needs to be supplied, so that sufficient oxygen should reach the metabolization site, or to the lungs, and that is a concept. So similarly, whenever there is a limiting supply of oxygen in a reaction, we require additional oxygen or external oxygen that needs to be supplied. Now, the molecular diffusion, and okay, so the MT actually it is denoted as an abbreviation of the mass transfer. So when we consider what drives this mass transfer, or how it occurs, the molecular diffusion is the movement of molecules from of a given substance from a area of high concentration to a area of or a region of a low concentration, that you know. So the term concentration gradient is used to describe this difference in concentration, and molecules will move from move in a direction which will eventually destroy this gradient. So which means if there is a movement of molecules from a region of high concentration to a low concentration, there's a tendency of movement of molecules from the region of high concentration to the low concentration, thereby creating a gradient. So initially some molecules will reach the lower region and there will be a gradient creation, and finally it will become reach a state of equilibrium, so that the final concentration will be distributed uniformly between these two targets. So that means at the first stage there is a high concentration and low concentration, then there is a gradient creation by movement of molecules from high concentration to the low concentration. Then at the final stage it will reach a state of equilibrium in which, so as I mentioned, there will be a creation of a concentration gradient initially during the initial stage of the mass transfer, and finally it reaches a stage of equilibrium. Now consider this case. This example. One second. Okay. So here a typical example of a gas bubble is shown here. So the gas bubble actually contains the air within along with oxygen that needs to be supplied or transferred to the site of utilization or the metabolism that is within the cell. So this represents the cell and intracellular portion, or the metabolism side is represented inside, and this is the bubble which contains the gas, that is the first region. So if you are discussing about the gas transfer or mass transfer of oxygen from the site 1 to the site 7, there are various stages where the concentration or the diffusion of the molecule, the movement of the molecules or the diffusion of the molecules will be affected differentially. So that needs to be addressed, so that you need to understand what are the factors that will affect from the movement of that will affect the movement of these molecules from the initial site, that is the gas bubble, to the final target that is within the interior of the cell. So you need to understand what are the different factors that will affect. So if you have a better understanding on these different stages of the factors and other things that affects the mass transfer, then you can design proper systems of reaction systems in which efficient mass transfer can be achieved, so that it will improve your process, overall bioprocess. So especially this is a part of the chemical engineering, where such reactor designs and their aeration systems etc. were designed accordingly. And even for a bioprocess engineer who actually conducts that bioprocess, he needs to understand these concepts, so that an efficient utilization of the resources in the reaction mixture is ensured only with the proper scientific understanding on this gas and mass transfer concepts. So you need to understand what are the parameters that affects the transfer of oxygen from the air bubble to the cell. So let us see what are the different phases that is involved in this stage. The first one is the bulk gas phase within the bubble. So the air is actually free to move. The molecules of air along with the oxygen is free to move within this air bubble. So because it's a fluid motion is there for the gas within. So that is the first stage. There is no other inhibiting factor that prevents the movement of oxygen within. And the second one is the gas liquid interface. As you know, for every say boundary, like you imagine the case of a lake or a pool or a glass which holds the water, where the liquid or the water, when it contacts with the surface or some shore or something, and at that stage there will be on the border or the boundary between these two phases, that is the glass and the liquid within. So when it touches the glass or glass vessel, there will be limited movement of molecules at that stage, whereas the other molecules which is away from the border will be free to move. So due to the surface tension and other things, there will be a limited movement along the border. So that is where that's what happens when there are two different phases will come in contact, and the molecules in the interface will have a separate mobility because of the surface tension and other difference in the surface tension, etc. Okay, so that is normally expected in every systems, and that's why you know that usually materials will come to stick on the border of the glass or the lake. Something will settle because of the limited movement or mobility of the fluid on this border. There will be settling of the particles around like that. So that's because of the difference in the movement ability of the molecules that is coming in contact with the phase. So you need there will be a separate movement or separate transfer efficiency at this phase. So that's why we are considering there is a gas liquid interface. And another one, there will be a liquid. Uh, the third one is the liquid film around the bubble. So the next one is the liquid film. That means this is the entire region is the broth. So, okay, you are discussing about the transfer of oxygen from a bubble that is present in the broth medium to the microbial cell present in the broth medium. So, the entire area that is represented as white is the medium. Both are suspended. The bubble and the cells were suspended in the medium. So, the region 4 that is marked here is the broth medium or the liquid medium in which the cells and the bubbles were present. Okay. So this phase, the third phase that is represented is the interface, or it is a film around that bubble. So the bubble is created by a film of liquid itself. Okay, that liquid film which actually covers the bubble, and that when the bubble moves, this film actually it is associated with the bubble and it moves along with the movement of the bubble, right? So there is this liquid film that is used for creation of the bubble will have another property or another movement efficiency of the molecules which will be different from the liquid. So that's why the third phase is the liquid film. So you have two liquid films. One will be around the bubble, and one will be around the microbial cell. So whatever different molecules like or the gas or the microbial cell or something else, if something is suspended in the liquid medium, there will be a formation of a film or a static film around that and that will have a separate mobility when we consider it or compare it with the additional liquid that is, or the entire broth medium that is present here. Okay. So we have another phase with a separate mobility, that is a liquid film around the bubble and the cell. The third one is the medium itself through which the oxygen needs to pass through and finally reach the cell. And there is another one that is a liquid and film interface. There is a liquid to film interface is there. And another one, there is a so the fifth one is a liquid around the microbial cell and the liquid cell liquid interface. So the next one, from this liquid biofilm, it needs to pass through the cell, and finally within the cell there will be another the cytoplasm or something will be there, and through which the oxygen needs to pass to the final site of utilization. So you can imagine various, at least 7 stages of oxygen transfer which will affect the concentration of the molecules present and the surface tension in between, etc., which will be different from one another. So that means you need to calculate all these things and consider all these things, and what will be the factor that will influence the transfer of oxygen molecules from one side to another. That needs to be calculated so that the final efficiency of oxygen transfer is all that can be calculated from this concept. So is it clear? So is it, hello?
Yes, sir. Yeah.
Oh, okay. So it is so simple because when we, in the case of a oxygen transfer from the bubble to cell, there are various phases where we have the gas is there, liquid is there, interfaces are there, cell wall is there, and cytoplasm is there. and everything will have their own difference in the overall transfer rate and mobility. Okay. So what happens in gas liquid mass transfer? So in case of gas liquid mass transfer, actually it is unusual as molecules have to move between different phases. So this difference occurs because why we are considering it separately, because all these are different phases where different molecules are there, different ability of the or different movement rates of the molecules are there present, or it is present in that different phases. So because there are boundaries and different type of phases are there. So the different phases and different boundaries are there. So transfer of these molecules through these different phases and different boundaries or interfaces, it is explained through film theory. Film theory attempts to explain the process of a diffusion of, let's say, oxygen from bubbles in the broth to the bulk liquid phase across the bubble interface. So you can consider it as say as a two components. For example, the gas from or the oxygen from the bubble needs to be transferred to the liquid first, then from the liquid to the cell. So this is a repetition process, because here also we have a microbial cell or a film around, and here we have the interior of the cell. So first step will be transfer from cell to medium, the bubble to medium, then medium to cell. So it can be divided into two parts, and that will be the second part will be a repetition. So the film theory actually it attempts to explain the process of transfer of oxygen from the bubble to the liquid through this interface, bubble interface. Now, oxygen is in much higher concentration in the bubble. You know that in normal air, we have 21% of oxygen in the air, and remaining is nitrogen and other components. And also, the air is sparingly, the oxygen is sparingly soluble in normal aqueous solutions. So the solubility of air as such in a liquid or the aqueous solution or in water is low. So which means therefore a considerable driving force is required to move this oxygen from the bubbles to the liquid. So to make that oxygen dissolved in the liquid medium or in the liquid or liquid broth, you require a considerable driving force. Means you have to pressurize it, or maybe you will increase the pressure, or a high concentration of the oxygen is required for transfer of oxygen molecules through this interface and make it dissolve in the in that liquid. So here we have the case of a transfer of oxygen from the bubble to the liquid. So since the partial pressure of the oxygen is normally, that's about 21% of the oxygen is present in the air, that is usually sparingly soluble, or normally it is not going to dissolve in the aqueous phase of the broth. So you require normally a high driving force, or a considerable driving force, or an increased pressure of the oxygen within the bubble is required to move this or push this oxygen out from the bubble to the medium and make it dissolve in the broth. Okay. So what and then means according to the film theory, as I mentioned, the turbulence in each fluid dies away as you approach the interface. It is I already mentioned that one, because throughout the interface of the bubble or the cell, where the gas phase comes in contact with the liquid, there is an interface. Where the cell wall comes in contact with the liquid, there is an interface of the or a biofilm around that. So in that region, there will be a limited mobility, as I mentioned. So the turbulence in that region will be less, that fluid movement or the molecule movement will be minimal. That means fluid dies. Turbulence in each fluid dies on the boundaries. As I mentioned in the example of a glass containing water, in which the boundaries or the of the glass and water will have a limited, and the molecules of water around the boundaries will have a limited mobility. Otherwise, the fluid is normally free to move. Whereas in the boundaries, the movement ability of the molecules will be minimal. A thin film of a stagnant fluid lies on each side of the interface. So that constitutes the film. And the only way through for oxygen is molecular diffusion, and in the previous session we discussed the diffusion or the convection and conduction, radiation, etc. So for a liquid molecule or liquid system, and in this case gas and the liquid, so the transfer of a we have only two phases, that is a gas and liquid phase is there, and in both cases molecules were free to move, and the free movement is not possible only in cases of metals, as you know. So molecular movement is possible in case of gas and liquid. So we have convective mass transfer through movement of molecules is possible in these systems. Okay. The concentration of any compound at the interface differs across the interface, even though the fluid at the other side of the interface are supposed to be in equilibrium. So uh, here throughout the interface the concentration will be different, so the exact amount of the molecules that is transferred from one phase to the other is not transfer or the same concentration cannot be expected on both sides. For example, you will have a 21% of oxygen in the bubble, and after the movement of these 21% through the interface, maybe the interface may acquire only 18% of oxygen, and there will be a maximum capacity in that phase. It will never acquire a 21%, and or similarly. And again, if you come to the liquid phase, maybe another the final concentration in the liquid phase may be 15%. So that will vary across the interfaces. Okay. So you can't expect the entire or the same rate of transfer normally if there is a different phase with the different properties. And this is simply due to the molecule's relative solubility in each phase, because the air is having there normally 21% is there, but in the boundaries there will the film around that air there will be another solubility and movement ability is there, and from the in the case of a medium into which it is transferring the nutrient broth or the or some other mineral medium or specially designed medium, etc. All these things will have their own solubility, and means the final concentration of or the maximum concentration of oxygen that can be achieved by the concerned medium will be different because of the relative solubility in that phase. So as you move away from the interface in either direction, the concentration of the bubble returns to the bulk liquid phase concentration, which is regulated through convective mass transfer. So final concentration of these air or the final molecular concentration is actually determined through, or it is regulated through convective mass transfer through this interface. So let's see the example here, or let's see how the film theory works here. Here we have the CAG, that means concentration of component A. Treat it as A as oxygen. Okay, concentration of oxygen in gas. That's how it is read. Okay, concentration of A in gas phase is the first stage. So this is the interior of the bubble where gas is present. Okay, from the interior of the bubble, and this region represents the that film around the gas, liquid film around the gas. Okay, so in the previous case, this is the first phase, and this film is represented as the second one, and the third one is the liquid. Okay, so we have three phases: first phase, second phase, and third phase. This is represented here. Okay, so that film is now divided into two parts. So one will be the side of the gas, and the other one is the side of the liquid. So the film will have two phases. The film is in contact with the bulk liquid phase and bulk gas phase. So there we'll have a separate transfer rates available in the film. So you need to calculate these two. Like this is the concentration of gas liquid interface. This is the concentration in a liquid interface. That is this is gas interface. This is liquid interface, and this is the bulk liquid phase or the medium to which it is transferred. So as I mentioned, the concentration, for example, here we may have 21% of oxygen that we are trying to transfer. but it will still decline because the maximum concentration of oxygen that can be transferred through this interface may be 20, and when we come to this interface it may become a further 18, so maximum possible is 20, and when we come to the bulk liquid phase, the maximum achievable concentration at this phase may be 15 because of the relative solubility of the molecules in that medium and further resistance posed by that medium, that phase interface. Okay. Now the term convective mass transfer needs to be understood. So by definition, mass transfer occurring under the presence of a bulk fluid motion is known as a convective mass transfer because fluid is in motion. Either it is a gas phase or here our material under motion is oxygen, for example. So that's a bulk fluid motion of oxygen is also possible through molecular movement of the convective process. So such processes where bulk fluid motion is available, where movement of the molecules is available through convection, and that type of transfer is known as convective mass transfer. Okay. So mass transfer between two moving contacting phases is present here. For example, in the bubble, we have a moving phase of gas within the bubble, and on the outside the bubble, we have a moving phase of liquid, or the both moving molecules of the liquid that is available on the medium. So the final transfer is the oxygen that is moving within the bubble is transferred to the transferred and dissolved in the molecules of a medium or broth medium that is moving outside. So we have a movement of molecules from a gas phase to a liquid phase. Okay, and both are moving. So that type of transfer is actually convective mass transfer. So the rate of mass transfer is directly proportional to the driving force for transfer and the area available for the transfer process. So we have two influencing factors: the mass transfer rate, or the transfer of say oxygen, that rate is directly proportional to the driving force. Driving force is the say partial pressure of oxygen or some high pressure or high concentration that can act as the driving force. And this driving force and area of transfer, or the overall area that is available for a mass transfer, that is the surface area that is provided by the air bubble. Okay, so that's these two factors who are affecting the overall mass transfer rate. So we have the transfer rate that is proportional to transfer area, which means the surface area of the bubble, and the driving force, that is the concentration or the pressure of the oxygen in the bubble. Okay, so it is directly proportional. The constant of proportionality is termed as the mass transfer coefficient. So we can say that when we consider movement of or convective transfer of molecules from one phase to the other, like a convective mass transfer, the transfer rate is directly proportional to the transfer area and the driving force that is available. And this constant of proportionality is termed as a mass transfer coefficient. We need to see some of the equations that is used for deriving these concept. Anyway, it is just for your understanding. You need to go into the go detail into the equation derivation of the equation. Maybe all are not well in mathematics, but I just need to familiarize you with the different terms that is involved and the different factors that is involved in the okay. As I mentioned, these the purpose of these derivations, or why I am showing these derivations, is just to familiarize you with the different components that is involved in the mass transfer process, so that you can understand the role of these components in the overall mass transfer efficiency. And for example, if you are aerating, or if you are deciding the partial pressure of the oxygen, or if you are adding more nutrients into the medium, or if you are changing the say viscosity, or if you are changing the medium with more antifoam agents, etc. So what will happen at that time by adding something? or by increasing the temperature, what will happen, or how the mass transfer convective efficiency will be affected. To calculate that one, you need to understand the different influencing factors. So that's why we are going through these equations, and it's not for the derivation purpose. You can just scan through that one, and you need to understand what are the factors involved. Okay, so is it clear?
Yes, sir.
Okay, so the derivation is not the important factor for a biologist, and that is actually more important for a chemical engineer or somebody who is designing the instruments and the systems. But our role is to understand the factors that is involved so that we can manipulate them properly. Okay. So, looking at the film theory, say I will show one or two slides, and then I will move to the last one, the final derived equation. So, you can look at the film theory. The driving force for mass transfer from a bulk gas to the interface can be expressed as. So, this is the first phase where from gas to the gas interface. So the gas to the gas interface, this is the driving force. So the driving force is equal to the constant K for G, that is gas phase constant, into area of transfer, and this is the concentration difference. So this is the gas phase concentration, and this is the gas interface concentration. Similarly, the driving force that is calculated for the transfer of these molecules through the liquid boundary, it is this is a driving force of a component A to the liquid is a constant liquid phase constant. Okay, the mass transfer coefficient at the liquid phase, and the area of transfer, and the difference like concentration in the liquid interface minus liquid concentration in liquid phase. So this is how the formula is derived. Okay, here the mass transfer coefficient of the or the overall, instead of considering the overall mass transfer coefficient for every interface or every stage of a transfer from one phase to another, it can be separately calculated. That is a for the transfer of molecules from gas to into gas interface, there is a coefficient and there is a calculation formula. From the liquid interface to liquid, there is another formula that is shown as second. And here A is the area or interfacial area for available for mass transfer, or the surface area of the bubble. Now, accordingly, this can be more simplified or derived by applying further simplification procedures. And I am not going into the further details. You will be provided with the PowerPoint presentation, and if you are interested, you can go through the derivation. And finally, the equations will be derived and combined. And now, when we come to this point, here we have, say, concentration of Ag divided by M. So this M, and I think this is better. Okay, this I think it will be explained here. It is important to eliminate CALI, that's a concentration of A in liquid interface, and CAGI, because this is the concentration of liquid interface, this is the concentration in gas interface. That is the film is divided into two parts. Okay, as I have shown. Okay, here this is the concentration of C or gas in the gas interface. This is the concentration in liquid interface. This is not possible to measure. You can measure the gas phase, or you can measure the gas phase concentration of the air can be measured, or the oxygen can be measured, and this can also be measured using some one or other form of instruments. But the film within the film or this interfacial concentration is not possible to experimentally prove. You cannot determine it. You cannot actually calculate it. So you cannot estimate it. And for that purpose, you need to eliminate that terms, because if you can't measure and compare, then it is better to avoid that term from the formula. So in that case, the first assumption we can make is that the interfacial gas concentration of the component in question is a linear function of the interfacial liquid phase concentration. That means, so here we have a interfacial liquid concentration, liquid interface, and this is the gas interface. So for simplification, you can say that say if it is having or say 90% of the gas from the gas phase is transferred to liquid interface. And from the liquid interface, maybe 80% is transferred to, or 50% of that is transferred to gas interface. So which means if the only 50% of this concentration is transferred to this one, you can say that the gas interface actually it is the liquid from the gas interface only 50% is transferred. So the liquid interface concentration will be half of that. So the M will become 2. So if there is only for 25% transfer efficiency from gas phase to liquid interface, then the N will be 4. So that means, so how much percentage of the component in question is transferred from one interface to another? Maybe that can be expressed in percentage. For example, 50% is transferred from one to another, or 25% is transferred from one to another. So in that case, you can say that it is a linear function of a gas phase concentration or the initial concentration. So if it is a 50% efficiency, or if the distribution factor is 50%, then that will become 2. Or if the distribution factor is 25%, or then you have to divide it with a 1 by 4, that is you have to divide it by 4, the M will be 4. Okay, so that represents, that M represents the percentage of the concentration that is actually transferred from one phase to another. So usually you can say that the gas will be gas interface may have 100% concentration, and from that only half is transferred to the other phase. So that is the efficiency, 50% efficiency, which means M is a 2. So only half of that gas phase concentration is transferred to the next phase. That's what it means. So that's the distribution factor. Okay. So likewise, you can calculate the formula. And finally, when we come to the concentration of A in the gas phase, and that it is transferred to the liquid phase or the liquid interface, and when there is a saturation state, and the saturation state it can be expressed in this as say this is a saturation state here. So here we have the concentration here, and it is not 100% transfer, and if it was 100% transfer, then that means there should be linear. It is not like that. So the final concentration or equilibrium concentration of A in this gas interface is a little bit lower. Maybe it's 90% efficiency. Okay. So if it is 90% efficiency, then this maximum concentration that can be achieved at this stage is known as a C star AL. So because if you consider the entire film interface and you calculate the C star AL, so this can be joined together, and you know that from the gas to the interface, so that's the first transfer, to the interface to the liquid, that is the next phase of transfer. So if 90% is transferred here, you can say that maximum achievable concentration in the interface is only 90%, and this maximum available percentage is known as a C star AL. Okay, so that's the equilibrium concentration. When these two phases are in equilibrium, that means after some time of transfer, this will this will reach a stage of equilibrium where we have a 90% concentration of oxygen here. So that maximum achievable concentration of oxygen in the interface is known as a C star AL, and from that only from the 90% only the concentration or the transfer is possible to the liquid phase. Okay, so here you can say that this C star AL is one important factor, and this is a concentration of a component at the gas liquid interface that is in equilibrium with the gas phase concentration. And a final representation is again derived here, and then finally you can say that here the overall driving force of A is a K of that is the mass transfer coefficient of a liquid into area of transfer into C star AL minus CAL. This C star AL is the concentration, maximum concentration available in the interface or that film. Okay. film around the gas. So that's C star Al. And this is the concentration in the liquid phase. So the overall driving force is equal to this product, that is a uh, mass transfer coefficient in the liquid phase, then area of transfer, that is the area of the bubble, and this is the concentration of the gas in the, or the concentration of oxygen in the boundary liquid, or that liquid film, and this is the concentration of A in the liquid or external medium. So here by step derivation you can reach up to that level. Now this you can skip that one, how the concentration is determined, oxygen concentration is determined within the gas or liquid, that is using a nitrogen purge, etc. You don't need to consider that one. So from after all these derivations and reaching up to this conclusion, or up to, this final equation, we have various factors like the mass transfer coefficient, the area of transfer, the concentration of concerned component in the interface, and concentration of the concerned component in the liquid phase. All these will be the various affecting factors in the overall mass transfer coefficient. So that's what we are concluding from that derived equations. So now we have to consider the C star Al. The C star Al is influenced by various factors. So from the equation, the overall driving force is actually directly related with the overall concentration that is actually transferred to the interface. From that only maximum possible transfer is possible to the liquid. The C star Al is actually affected by various factors like gas pressure and the oxygen partial pressure. So instead of 21% oxygen, if you have 30% or 40% oxygen, you will have a better driving force because there is a high concentration of the oxygen. Subsequently, that will be transferred with better efficiency into the interface and concerned liquid. So one of the major factors is the gas pressure, or overall gas pressure, and the partial pressure of the oxygen, and the concentration of oxygen within the gas itself. And that is one of the factors that is influencing this. And the second one is temperature, and the third one is solutes, presence of solutes. And there are some other factors that affect the KLa value also. So the KLa is another component of the equation where we have the mass transfer coefficient of the liquid phase into the area of transfer. So that's the KLa value. It is affected by the antifoam agents because it affects the formation of the bubbles and the surface tension, and even you know that if you add the antifoam agents, the bubbles will not be formed, larger bubbles will not be formed, or finer bubbles will be produced. It will affect the overall surface area of the bubble. So antifoam agents will normally, it prevents the bubbling. So the result is the change in the surface area and effective and the overall mass transfer coefficient of the bubble. Okay, so these are the different factors that can have direct impact on the overall mass transfer efficiency. Now, if you understand this concept, you can decide on what is the partial pressure, or how much oxygen is to be supplied or air should be supplied, and what should be the purity level of the oxygen, and what is the temperature in which the fermentation is to be conducted, and what are the solutes that will be that will favor a proper mass transfer or oxygen transfer in the system, and whether antifoam agents can be added or not, and if so, what should be the optimal concentration of the antifoam agents, etc., can be calculated in a fermentation reaction if you understand these concepts. Now we'll come to the gas pressure and oxygen partial pressure of the gas. That's the first category that is affecting the say C star Al value. Okay, the equilibrium relationship between oxygen partial pressure in the gas phase and the liquid saturation concentration, liquid saturation oxygen concentration can be described by the following relationship. So the equation is shown here. Here we have the partial pressure of A, or oxygen in gas phase, is equal to the product of the total pressure of the gas into the mole fraction of the oxygen in the gas. And so this is the equation. So this is the total, the partial pressure of oxygen in the gas, and that is actually the driving force. Okay, the concentration of the oxygen, and that can be calculated with the total pressure of the gas into the mole fraction of the oxygen, or A represents oxygen. Okay, and this product is the overall driving force, and we can have a constant that is H into C star Al. So this is the equation. This H is known as a Henry's constant. So these are the different terms. This is the partial pressure of oxygen. This is the pressure of the total pressure of the gas. This is the mole fraction of the oxygen or the concerned component in question, and which will be equal to H, a constant, into C star Al. H is the Henry's constant. So this is the equation, and here the various factors that is actually directly related is the oxygen partial pressure is the driving force, because if there is a oxygen high concentration of the oxygen within the system, instead of 21%, if we are 40 or 50%, it will have a better transfer efficiency, as I mentioned in the case of the oxygen supply for a medical patient, like that. And this is the total pressure of the gas within the bubble, and this is the mole fraction of the oxygen in the gas. So these are the different components involved in the question, and it's also described in the text also. And obviously, by increasing the partial pressure of the oxygen, so if you increase the partial pressure of the oxygen either through enrichment or by general pressure increase. So you have two options here. There are two components. To increase the partial pressure of the oxygen, you can either increase the total pressure, you can supply pressurized gas, or you can supply, you can increase the concentration of oxygen molecules in the gas by just oxygen concentration. For example, instead of supplying air, you can connect an oxygen cylinder. So you will have a high concentration, or the mole fraction of the oxygen will be high if you are directly providing oxygen, pure oxygen, or a high concentrated oxygen. That means this component will increase, effectively increasing the partial pressure of oxygen. Or you can increase the overall pressure of the gas. A pressurized gas can be given, which will also increase the concentration of which will also increase the driving force. Okay. So obviously, by increasing the partial pressure of oxygen, either through enrichment or by general increase in the pressure, that is this component, total pressure, it will lead to higher saturation concentration of oxygen in the liquid phase. So if you want to achieve a high concentration of oxygen in the liquid phase by increasing C star Al, then you need to either increase the pressure of the total pressure or increase the concentration of the oxygen by purifying it or by supplying pure oxygen. So the next phase is temperature. Then increasing temperature causes C star Al to drop. So it will decrease the C star Al value or the concentration in the liquid phase, or that interface will be reduced by increasing temperature. So that the driving force for mass transfer is reduced. So the overall, if you increase the temperature, the mass transfer efficiency will be reduced. So that's the concept. So you can see some of the examples where 25, the temperature is 25 here, and here it is 30. Saturation concentration will actually reduce when you increase the temperature. So accordingly, the Henry's constant will also vary. Okay. So above 40 degrees Celsius, the solubility of oxygen significantly drops, which means your fermentation or your mass transfer efficiency of oxygen in a fermentation or a reaction will be significantly affected by the temperature or increase in temperature. And if you are preferring a lower temperature like 25, it will be better. So if you increase the temperature, maybe you may require such cases where you are working on some thermophilic organisms or something where you go for 45 degree or 50 or 55 degree cultivation, etc. That is possible, but in that case you have to take into account of the oxygen transfer efficiency, because you have to adopt additional better methods of oxygenation so that proper oxygenation is ensured in that system. Because due to the increase in the temperature of the reaction or of the culture medium, you have a lesser oxygen transfer efficiency, and you have to see that the overall oxygen present in the medium or supplied to the medium is actually not reaching the cell. So that's why, because of these increase in the temperature, that affects the C star Al value or the oxygen concentration of the interface. Now the third component that we mentioned is say that is solutes. The fermentation media typically contains significant concentrations of salts, sugars, and other dissolved components. So they actually constitute the solutes. The presence of such solutes has a significant impact on solubility of oxygen at a given temperature and pressure. So these solutes is having a significant impact on the solubility of oxygen. So the solubility of oxygen decreases with the increasing concentration of solutes. So like that of the temperature, the increasing solute concentration decreases oxygen solubility. So oxygenation will be difficult if you increase the solute concentration further. The saturation concentration of oxygen can potentially decline by 40 to 50% in typical fermentation media over that of a deionized water in the same environmental conditions. So if you can see that typical fermentation media actually contains a lot of solutes or other components are there. So about 50%, 40 to 50% reduction is there for saturation concentration of oxygen when we compare with the deionized water of the same environmental conditions. So water actually, since it doesn't contain much solutes, the better oxygen transfer efficiency is possible through that deionized water. But when we produce a medium out of that with by addition of a lot of solutes, then your oxygen transfer efficiency may be declined by 40 to 50%. So temperature increase declines efficiency, and solute increase again decreases that oxygen transfer efficiency. But you have to add the solutes or you have to add various media components. You can't avoid them. But in that case, based on the overall efficiency and the solutes that is required for the normal fermentation, based on that one, you have to design a proper oxygenation system by controlling the other factors like the oxygen partial pressure or the aeration system, etc. A better aeration system needs to be provided so that sufficient quantity of oxygen is delivered into the target site. So for that, you require a better understanding on the various factors like the aeration efficiency and the solutes and the temperature, etc. that is directly affecting that concentration, equilibrium concentration. Now, the third one that is mentioned is, sorry, the next one, that's the fourth one, that is actually, it is affecting KLA, that is the mass transfer coefficient into the area, and that is the KLA value. So that KLA value is affected by the antifoam agents, and most fermentations end up producing agents that produce, one second, agents that produced fermentations end up producing agents that produce and stabilize foams such as proteins, polysaccharides, and fatty acids, etc. So the proteins, polysaccharides, and fatty acids that is produced within the fermentation medium during the process of fermentation, actually they are the agents that so they are actually stabilized by the fermentation process, which will result in foaming. Okay. And most fermentation engineers will deploy antifoam agents in anticipation of this problem. So antifoam agents in general reduces the surface tension in the foam, generally causing the foam to collapse. So antifoam agents reduce the surface tension, and thereby it reduces the overall size of that foam, and thereby the foams will collapse if you are adding antifoam agents, and it will break into tiny small bubbles. So reducing the surface tension generally results in smaller bubbles. This may initially be seen as a good for KLA. That is a KLA, as I mentioned, that is a liquid phase mass transfer coefficient into area. So since the bubbles, larger bubbles, were broken down into finer, smaller bubbles, then you may think that smaller bubbles actually, that smaller bubbles were providing better surface area. Instead of a larger bubble, if you are breaking that into small bubbles, then certainly that means your surface area A is increasing. So initially we see that, we may think that since you are breaking down that larger bubble into finer bubbles, and it will have a better effect because A will increase because of the increase in smaller, because of the surface area increase provided by the smaller bubbles or finer bubbles. That may be a better one or a better option. You may think like that. So it may initially be seen as a good factor for KLA. The interfacial area is increased by having more smaller bubbles. So that's why it is mentioned. However, the interface mobility of the bubbles is significantly decreased by the antifoam agent, resulting in a decrease of the KL element. Even if the A is increased, the Kl element will be sufficiently decreased or significantly decreased by the antiform agent. So if the Kl value is decreased, then it overcomes the overall increase of the A, and thereby the final decrease in the overall Kla value. So the antiform agent or addition of antiform agent, in effect we can say that it will have an adverse effect. So it increases the K and decreases Kl. So the decrease in Kl will have more impact on the Kla value than that of the effect that is contributed by the increase in A. Okay. So resulting an increase in Kl element, and the decrease in Kl generally outweighs the increase in A, resulting in a net drop in the gas liquid mass transfer coefficient. This can often be up to a factor of 10, about 10 times reduction in the overall Kla value can be expected if you are using large quantities of higher concentrations of antifoam agents. So this is how we are summarizing the mass transfer of a fermentation system. So now we understand what are the different factors that affects the oxygen transfer in or mass transfer in a fermentation reaction. Especially our focus point, whenever we are talking about a mass transfer, we are talking about the oxygen transfer of a fermentation. So this is the concept, and now you understand what are the different factors that is involved, which includes, initially the partial pressure or the driving force. Driving force means the pressure of the oxygen and overall pressure, which drives that oxygen out of that air bubble and make it or force it to dissolve in the medium, and subsequently from the medium it will be forced. The high concentration of oxygen in the medium will be driving force for penetrating it into the cell and thereby making it available within the cell. So at two stages we have oxygen transfer that is occurring in a fermentation reaction. So the overall driving force will be the partial pressure or the high concentration of oxygen. So that's the significance of a sufficient quantity of oxygen that will be provided through aeration. Okay, and the second one is temperature. By increasing the temperature, the efficiency of oxygen transfer will be reduced. Now we understand that. And the third one, that is the increase in the solutes. So if you have anyway, if it's you are adding more and more, a very crude concentration of the medium is prepared, then naturally the oxygen transfer efficiency will be reduced. So that's why we are optimizing the medium. The medium should have an optimal concentration of the media ingredients, and usually there are statistical methods for optimizing the medium. So instead of say you are adding 1% of a component, you are adding 10%, then you will make it more turbid, and the fermentation will be adversely affected if you are adding high concentration of the concerned component. This is because it may affect significantly the oxygen transfer efficiency of the medium. So that's how. And if you are going for a continuous fermentation, you will supply the medium with further ingredients at later stages of fermentation, not at the initial stage. Thereby, if you are continuously supplying nutrients into the medium, then thereby keeping the overall concentration at 1%, that you can do. But instead of that, if you are adding all the ingredients at the same time, just like a batch reaction with a very high concentration, that will have the adverse effect because of these effect of solutes. And finally, I have already discussed the factor that is affecting the KLA value, that is antifoam agents. Antifoams decreases the surface area by breaking down the bubbles into very finer bubbles, thereby increasing the surface area, overall surface area available for transfer. But that is actually outweighed by the significant decrease in the mobility of the molecules, and that affects the KL value, and that means the mass transfer coefficient of the liquid will be significantly reduced, thereby decreasing. About 10 times decrease can be observed in case of such a antifoam agent addition. So if you are going for a fermentation, certainly you have to add some amount of antifoam agents, but it should not be excess, because only up to the required level you have to add. Otherwise, so that there will be a balance between the form reduction and the subsequent oxygen transfer rates or the KLa value that needs to be addressed. So, is there any questions?
Sir, ഇതിന്റെ reference ഒന്ന് പറഞ്ഞു തരാമോ?